The next MIT faculty speaker is SARA BEERY. SARA is Assistant Professor of AI and Decision Making at MIT Department of Electrical Engineering and Computer Science. Deeply passionate about the natural world, SARA is driven by the growing need for technology-based solutions to pressing conservation and sustainability challenges. Her research centers on developing computer vision method to enable global-scale environmental and biodiversity. Supported by NSF, NASA, Google, Microsoft, IBM, the US Air Force, and so on. SARA will talk about monitoring urban nature, the role of AI and digital twins in tree health monitoring. Please use Pigeonhole again for your questions, and join me welcoming SARA to the stage.
Hi, everyone. So I lead a research group at MIT that really focuses on what we call application-driven innovation in AI. And this is really, for us, kind of a reframing of how we think about the development of AI technology and really significantly grounding those technological developments in some of the big societal and environmental challenges that we're facing. So we work on everything from wildlife in Africa to large-scale estimates of forest carbon to actually looking down to the scale of insects or even genetic diversity. But today I'm going to talk about one specific project, one specific dimension of sort of this goal of being able to understand the global nature system really comprehensively across scales, which is looking at the level of cities and trying to better understand and better measure and also predict into the future what urban forests can do for us and how we can actually improve the quality of our urban forests to improve the quality of life of the people and infrastructure within those cities. So this is an example. This is taken within a city. This is in Pasadena in California. It's a part of sort of the larger city of Los Angeles. And you can see here that this is an example of what I would call a very healthy urban forest, right? There's so much green here. And what is this urban forest sort of providing to the people who live in the area? So there's actually been a pretty significant estimate of the different types of benefits that we receive from green space, including urban forests in our cities. This can support biodiversity within your city. So actually the trees provide sort of the foundation of local habitat for many of the other species that we as humans coexist with. They reduce air pollution. They've been estimated to remove something like almost 800,000 tons of air pollution annually. They sequester carbon, and actually the total opportunity for additional carbon sequestration is something from 1 to 2.4 gigatons. They reduce energy use, building energy use, by essentially helping with sort of overall cooling, as an example. One of the things that I think is very important as we're moving into, unfortunately, a lifetime of climate extremes is the reduction in extreme heat islands provided by the shade and evapotranspiration that these trees are incorporating into the environment. And we've shown that trees in a community is correlated with lower asthma rates, reduced hospital visits during heat waves, improved mental health. So people thrive when they're surrounded by trees and nature. But unfortunately, what we really see almost everywhere on Earth is that those benefits of urban nature are really not universal. So I showed you that picture of on the ground in Pasadena. That's where I did my PhD at Caltech. And you can see on the left in Pasadena, you can see from satellite that increased cover of green space and trees. Now, if you go to Carson, which is quite nearby in Los Angeles, less than 5 miles away, all of a sudden you start to notice that green space is significantly less. And I'm sure all of you can guess, Carson is an area that is not as wealthy, that is not as white, And these types of trends are kind of unfortunately seen globally. So what we're seeing is a lack of equity in access to green space, which also means a lack of equity when we think about the experience and the infrastructure and the investment of resources in our urban spaces. And so one of the things, and this was in partnership with Google, I did my postdoc at Google, we've been doing is building systems that help cities more quickly and easily access information about tree canopy cover. And we've been building very high accuracy, high resolution maps of tree canopy cover for now we're close to 1,000 cities globally. And how does this get used? So now you can build these heat maps of kind of where and when you see the most tree canopy cover, but in the United States, we're actually also directly partnering with policymakers. So for example, Tree Equity Score, which is a system that actually directly predicts a score for the equity of the urban forest across different areas in a city, and then can produce an overall score for the entire city of how much difference in equity there is in these different areas. Right, and so now you can imagine if you're a decision maker or if you're just an advocate on the ground, access to this type of information and data can really drive policy. It can really help you fight for increased equity, for increased investment of resources, and to improve your sort of urban landscape and your urban forest in the areas you live in. But it turns out that just looking at tree canopy cover really isn't enough for us to truly understand these complex natural systems. So we actually need to know instance locations. So this means the locations of individual trees, and we need to identify which species they are if we want to be able to, for example, estimate water retention in a flood, or the amount of carbon that is sequestered now, but also the potential carbon as those trees grow into the future, to estimate the potential for heat reduction, because individual species correspond differently in terms of their heat reduction potential. Easy example here, a palm tree doesn't really do much in terms of heat reduction because the canopy is very small and very high up. They can help us monitor species reaction and resilience to our changing climate at scale. One of the things that I think all of us are going to have to grapple with is that our environmental niches, our kind of environmental envelopes are shifting quickly. So the species that are thriving now in Los Angeles may not be the species that are going to thrive 20 years in the future. And Los Angeles has really been thinking about this. All of you, I'm sure when you think about Los Angeles, you probably think of palm trees. Los Angeles as a city, their urban ecologists have actually made the pretty strong decision about a couple years ago to no longer plant palm trees when those trees die. And that's because they aren't actually native to the area, and they take a lot of water and don't provide a lot of these ecosystem services. So the interesting thing you can start thinking about is how to not just try to improve your current forest, urban forest, you can also plan for the future. Plan for the likely climate extremes and the climate sort of envelopes that we're going to be seeing, and target the planting of specific types of trees to provide the benefits that are going to add most value and stay resilient and robust into the future. So we can strategically plan our planting to sort of maximize the benefits and also maximize biodiversity. And that includes not just the tree diversity, but the diversity of all of the other species we share our cities with. An important example here is insect pollinators, which are a really vital component of a maintained and successful system. So, how do we do this now? Cities invest millions of dollars into what are called tree censuses. So these are, they basically go around and they map every individual tree and species, specifically focusing on public trees, which is the trees that the city is required to manage. So this is a map from Seattle of the 10 most common genera of trees. I grew up in Seattle, so actually within the confines of this map. And what you can see is, okay, yep, there's a pretty good amount of diversity, but also there's a lot of trees here. And then one of the major things that cities need to do is they need to decide how to invest their resources to help manage these trees. So, where do they go? What do they need to prune? What do they need to replant? Which trees are going to die and potentially fall over and damage infrastructure or human property? But those tree inventories, like I said, they can cost millions of dollars. And as a result, they tend to happen maybe, if you're lucky, once every 10 years, right? So you're going out, you're going to pay millions of dollars for experts to drive every city street and map every single tree. These tend to be out of date, and they also tend to be limited in scope. And if you sort of looked at that previous equity map, I think you can probably guess which areas of the city are most likely to have accurate, up-to-date data on their urban forests. It's the areas that have usually more wealth. So what we've been doing is trying to figure out how to automate this process of detecting, categorizing, and monitoring urban forests. And this is in partnership with teams at Google and at Purdue. And so as a starting point, we built a data set for 2.6 million individual trees across cities in North America. And we created this entirely using public records. So actually these published examples of tree censuses. And I think the interesting thing here is because we're at Google, we're leveraging, and one of the reasons I built this project at Google, is we're leveraging a bycatch from data that Google had already collected. So for every single tree, what we're doing is we're capturing both aerial views of the tree, so these are aerial imagery, but we're also leveraging Google Street View data, because Google has collected and accurately updated ground level images for almost every tree on Earth in a city over the last few years, right? And this is data that they'd already collected, and now this is a co-benefit that we can get without actually paying for any new data. And one of the things that makes things like biodiversity or tree species identification so difficult is that it's long-tailed and fine-grained. So what does that mean? It means the vast majority of trees in cities are about 5 to 10 different types. And then there is this incredibly long-tailed distribution of trees that are increasingly rare. And then, I don't know, how many of you in this room know how to identify different species of trees? Anyone? Hey, that's amazing. Okay, usually I get like no hands. So there's a couple people. So we can ask them, and they can tell us, but you can imagine that actually, you know, this is not the type of labeling that you can crowdsource easily, because tree species look similar, and there's actually not a lot of expertise in this space. And these are things that are really hard for AI. AI is good at stuff that is easy and common. It's good at, for example, using computer vision, distinguishing between cats and pizza, but it's not necessarily good at telling the difference between individual species or even individual genera, genuses of trees. So what do we find? Well, one interesting thing, and I think a very interesting thing when we're sort of reflecting on the success of these machine learning systems and the type of data infrastructure that's useful and required, is we really do see significant benefit of pooling data across cities when we train these models, right? And we kind of know that AI is data hungry, like this is a kind of common thing. Now, I think there's two important trends here. So what we're looking at is the performance of tree species detection and classification accuracy for different cities. And then the blue is if you train just on the cities. The orange is if you train regionally. And the green is if you train sort of globally, though in this case it's just all North America. There's a huge boost. There's a huge difference in performance when we move from very local to more regional training. The relative benefit of going to that sort of global training is kind of small. And I think what we've reflected on, what we've seen in the biodiversity monitoring space overall, there's a lot of complexities when you talk about sharing data or publishing data, right? And this is also true for companies. And I think we need a better understanding of relative value of data, because I don't think we need global infrastructure for everyone to share data to really see the most maximal benefit for individual users. There's a huge amount of value in finding your nearest peers, finding the sort of systems, the companies that are most similar to you, and then thinking about how to strategically share information across those things to mutually benefit, instead of trying to, build some sort of pie-in-the-sky global data sharing infrastructure that, while it sounds nice from a bureaucracy and policy and regulation and data ownership perspective, is a bit of a nightmare. So what is one of the reasons that this might be occurring, that we sort of see this regional benefit that's pretty significant versus the global benefit? So here I'm mapping out the 20 most common genera of trees for a bunch of different cities. And one of the things you can kind of see, even just at a gut check, is that the colors are kind of shifting and different, right? And this is capturing the differences in the distribution of the types of trees in these different areas. And I've actually, in sort of my machine learning work, I've spent a lot of time thinking about distribution shift in data and how that influences and affects the performance of machine learning models. And this is just kind of one example of many that I've seen where we really do see, again, that similarities in the distribution of what you want to predict on are pretty tightly correlated to improvements in performance. So on the left, we're looking at just the distance between the distribution of trees in any two cities. You can kind of see these blockwise structures that are somewhat regional. You can see that, so here I think basically higher is they're more far apart, and darker is they're more close together. So for example, if you just look in the top, Vancouver, Surrey, Seattle, these have very similar distributions. And then on the right, what we've done is a systematic analysis of the co-benefit of or the generalization capacity if you train on one city and evaluate it on another one. Basically, how far can you get these models to stretch and still have value? And what we see is that it's kind of an inverse. There's some interesting patterns here. And you can see at the bottom, as we kind of go regionally and then we move up to globally, that you really are starting to see these patterns emerge, where similar distributions, similar sort of challenges end up resulting in more generalization capability and more sort of reusability of these models. And it can also help us think about, say you have a current set of training data, you have a current set of places that you're exploring. Where are we likely to be able to trust these models? How do we think about measuring the similarity between different deployments or applications of AI to think about where we're likely to fail? I think these types of insights around distribution are really important when you're trying to actually deploy AI in real-world scenarios where they're high risk, where performance really matters. In terms of even thinking about whether the investment is worth it, right? Is the existing set of training data likely to be matching your use cases well enough that you hope to see performance be at least in the realm of usability? And then I really do think it's important to kind of emphasize that diverse large-scale data curation is pretty universally valuable. Some cities are kind of more generalizable than others, but really training on all cities, like if you can kind of maximize the generalizability or the diversity of your training data, you really do see that generalized best across as many of these different cities as possible. And then there's this other question of how does these different modalities, this aerial view versus the ground view, influence results? And we do find that combining these different views using regional, so sort of specialized to the more regional characteristics, mixtures of experts, give us better results than a global specialization. So when you're thinking about kind of digital twins, actually in this process, we're using a mixture of experts model to combine information. That's actually really, it's important to specialize the kind of mechanisms you use to combine information as well as the models you're using to predict information. So looking to the future here, I think we've talked a lot about different ways to think about modeling the world and these different pieces, and I've only really just been talking about how do we identify, how do we build a census for these trees. But, if we zoom out, we have trees on the street, but there's also a lot of other trees in the city that are not public trees. So one thing that I think we really need to start thinking about is if we're trying to understand the benefits of an urban forest, we need to include public and private trees. But we also need to understand more than just where it is and what species it is, right? We need to be able to measure health, structural integrity, potentially predict growth. And I think this kind of brings up this idea that we need to generate potentially realistic digital twins for every tree. So now if you're talking about a digital twin, I think the important thing to remember is that these can happen really across scales. We can build a digital twin of the Earth and the forest systems globally, and then we can zoom that in to sort of the forest systems in a country like France. We can zoom that into a city like Paris. We can zoom it into a neighborhood, and then you can actually also kind of have this twin of even every individual tree within a neighborhood. And of course, the computational complexity can grow exponentially. So then again, having even systems where we can start to approach digging into this and understand where it's worth that investment of additional computational complexity at these different scales, I think is really important, and I don't think we're really there yet for most of these systems. But how do you actually generate a digital twin of an urban forest at the level of individual trees? So what we've done is we've started from these ground level images that we're getting from Google Street View, and then we've leveraged modern AI technologies, so these are technologies like diffusion and NERF, to generate an envelope, a likely 3D structure of each individual tree, just from those monocular ground level images. And then we've leveraged the sort of state-of-the-art in synthetic tree monitoring, or modeling, coming from the graphics community. So people who are building, for example, all of the unique trees that you'll see in the background of video games. And we're actually growing trees based on the growth characteristics that are measured in practice into those envelopes, conditioned on the specific species of tree. And so how we're actually doing this, right? Okay, so we have an image. We're building essentially 2D and 3D priors using diffusion. So if any of you have not, or aren't really familiar with what diffusion is, probably the way that you've interacted with diffusion the most in the last couple of years is through, for example, text-based image generation. So if any of you typed into SARA or Stable Diffusion or something, make me a picture of a cat in space, and then it'll generate an image. That image generation process is using an AI system process called diffusion. We're taking that same process, but we're actually using it to generate 2D and 3D priors over the shape of trees for specific species. And then we're conditioning that on an input image, and then we're generating both this NERF-based envelope and then what we're calling the digital twin, which is this likely actual morphology of the tree based on known growth parameters of different types of trees. And then the way we're doing this is we're building in these synthetic tree models from the graphics community. So what does this let us do? Well, one thing is, if you compare to previous sort of estimates of tree 3D shape, ours is doing a lot better. You can go check out the paper. These are just kind of interesting examples of kind of known failure modes. If you're doing this from a single image, right, you don't want the back of the tree to be estimated to be flat. So that's where those 3D priors are quite helpful. We don't often have flat trees. But then what does this digital twin give us? Why did we want to do it this way instead of trying to do it sort of from AI-based principles alone? So the first thing is, because we have these growth-based algorithms that are generating the morphology of these individual trees, this means that we can then, taking that growth model, shift in both time and space. So we can have the leaves be on or off the tree. We can estimate the shadow structures underneath. And then we can predict how this tree will grow into the future, right? And they have realistic growth conditions, right? So they'll grow around buildings or structures, and they sort of respect boundaries as they're growing together. And so now this is, I think, important because a lot of the things that city or urban planners really care about are things like how much urban heat reduction does this tree potentially provide? Or how much is this tree likely to grow in the future? And how can I sort of measure that growth? We'll use diameter at breast height as a really common measurement of a tree, and that's tree's sort of health and growth. And so what we've done is we've shown that actually we are doing a reasonably good job of estimating these parameters directly using these digital twins of individual trees. And we can actually estimate the differences, and they seem to match pretty closely in reality between sort of winter and summer shade. So I think this is important. And we've now done this for about 1 million trees across North America. So we have these individually conditioned, representative digital twins of 1 million trees. And I think it's kind of just the start, because now when we're talking about planning for the future, infrastructure, we can start thinking about when and in what ways do we need this level of specificity in our digital twins, right? So if you're thinking about a new planning project and you want to think about what types of trees to plant, well, one thing you can do is you can build these sort of estimated digital twins for other trees at different ages within your city to get an estimate of what the likely future growth of those trees you're planting are based on the relative conditions that are relevant from your city, right? Because trees grow differently in different parts of the world. And then zooming out from just trees, I think it's quite important to not forget that we are not the only species on Earth. And we're currently facing what's being termed the 6th mass extinction of biodiversity, right? So many of you have probably heard this term thrown around. The UN has proposed this big global biodiversity framework to help us address this by 2030. But we're seeing extinction rates accelerate exponentially across every taxonomic branch of biodiversity. We've lost about 70% of all wildlife on Earth since 1970. And our current extinction rates for species are faster than the last extinction of the dinosaurs. So we're living through this crisis. And I think that we need to not just think about this kind of 30 by 30, which is this big biodiversity policy that's been set to try to protect 30% of the Earth's species by 2030. We have to think about the other 70%, right? We need to think about the ways that we can support nature and biodiversity in the spaces we live in, because we need to coexist. We need to have sort of space and kind of co-benefits as we move forward as a society if we want to be able to prevent pretty catastrophic extinction. So, happy to take questions.
Okay. What mechanisms are being developed that could help companies measure, report, and reduce their biodiversity and nature impact?
Yeah, that's a great question. And this is something that, especially for all of you here in Europe, it should be of increasing concern because the regulation is coming. There's now biodiversity impact assessment built into a lot of the regulatory policies that are being implemented across Europe. So for example, there's a big, if you're doing any sort of large-scale development project within the EU now, you need to report on the biodiversity impacts of that development project. So there's a couple of really useful frameworks here. There's something called the Task Force for Nature-Based TNFD, Financial Disclosures, and that came out several years ago. It provides like sort of a starting point framework for companies to think about how to sort of self-reflect, assess what their nature risks are, what metrics are appropriate to use to report on them, and how to move kind of forward in terms of making a plan for a sustainable, nature-positive future for their company. But I'm actually really excited about a much more recent framework that came out just last year in 2024, which is called the Science-Based let me see. Anyway, I'm gonna mess up these acronyms. Essentially, in 2024, there was a new framework that was just released for companies that's all based on really nice, like scientific regulatory frameworks. But I think the thing that people don't understand is that we don't have the right information yet. We don't have the knowledge about, we don't have the data collection systems to understand biodiversity impacts as effectively. So one of the things I've been pushing for a lot, if you're thinking about sort of your impacts as a company, is the need to think about measuring systems and the potential added value of contributing nature-based information back into the global system. So I think, with a bunch of others and with the United Nations Convention on Biological Diversity, we've been trying to understand what it could look like to build data markets around nature that companies can contribute to. So if you're thinking about your biodiversity positive sort of work, you can think about, for example, actually directly reporting on your own impacts, but also you could think about providing new information. So for example, supporting conservation organizations or countries where we're lacking a lot of information and generating the information necessary to better improve our impacts. So actually data as a sort of first-class citizen in the sort of efforts to work together.
Okay. The next question is, how can companies prepare for recent and future regulation around biodiversity and nature?
Yeah. So I mean, I think those two different frameworks I talked about are a really nice starting point. But I would be aware that particularly in the EU, like these regulations are coming, right? The Convention on Biological Diversity requires that all companies, so this was the Keynote Montreal GBF, it was agreed upon by a bunch of nations, including the EU, all companies are going to be required to report on their biodiversity and nature impacts by 2030. So you have 5 years to figure out how to do it.
Okay. And would using collaborative labeling with the expert verification be feasible? A similar app called INPN in France does this to catalog and map biodiversity.
Yeah, so there's INPN, there's apps like iNaturalist, PlantNet is a really big one that's actually based here in France. Alexis Joly down in INRIA is sort of the one that built PlantNet. Absolutely. And I think this is one of these really interesting questions when we think about AI systems overall, is like, where and in what ways and whose expertise needs to be injected in which parts of the system to build things that we can trust. And I think for me, I've been thinking about that expertise in increasingly sort of diverse ways. So for example, just next week, we're presenting a paper at one of the larger computer vision conferences, ICCV, about how experts can actually very quickly determine which model in a set of models is going to be best for their use cases. And so I think instead of just thinking about injecting expertise for training, we need to think about injecting expertise for evaluation, for calibration, for uncertainty estimates, or even for direct estimates of inference. So for example, things like prediction-powered inference, where you take an AI model that you know is imperfect, and then you build the right statistical framework around it so that you can get robust, unbiased estimates of the true values that you care about, regardless of the bias in the original AI model. So I think, the predictive models themselves are just one piece of a much bigger system when we start thinking about deploying these in the real world. And I think there's a lot of potential to start thinking more and more creatively about whose expertise gets injected at which points in the system, and where that adds the most value in terms of the things we actually care about, these downstream things like estimating species distributions globally, or, for example, estimating when your blades are going to fail within a machine learning manufacturing system.
Okay, thanks, Sarah. I think we should stop here. Thank you, Sarah.
Yeah.
So we are running a little behind the schedule, so we're going to have 23-minute break, coffee break. So please use this opportunity to network with MIT people and also with other industry members. If you have any questions about MIT ILP, please talk to us, Gayatri, Jose, and me. And please come back by 11:25 a.m. Thank you.